Welcome to physical chemistry. If I seem a little bit annoyed, that's because I recorded this 3 times and it messed up. So, let's get on. What I'm interested in today is the electromagnetic spectrum. I'm going to send you to Wikipedia to have a look at that. There's a better picture than I can draw. I haven't got other equipment today to show you that, so I'm going to leave it. But let's have a look. This is the equivalent, just drawn in not so pretty, starting at long wavelength with radio, coming a little bit shorter with microwave. 5G is the new communication standard, which is on the end of microwave. Thinking about the radio, that's a very long wavelength piece of radiation, and so we can imagine that for chemistry it's not particularly interesting because the wavelength is bigger than most containers. It's in the order of meters, sometimes even longer. When we come down to microwave, we know that it can heat things up in our microwave oven, for example, and some people get worried that the 5G towers will do some kind of damage to them. But what is the microwave energy actually doing? Now, in the microwave, the electromagnetic energy is pushing ions, mostly water, and also sometimes electrons to and fro, because that's how the energy comes. It comes as an electromagnetic wave, so it can push electrons around, or it can push charged things around. If the space that the ions have got is big enough compared to the microwave, they can absorb it and be pushed around, and they can heat up the substrate, heat up the whole thing, because they're sort of pushed bash into things as they move around. Likewise, if you look up Steve Mould, so sorry, I was going to put a link, but I've run out of patience today. If you look up Steve Mould, or you look into my playlist for physical chemistry, you can see Steve Mould. He's a sort of YouTube scientist. He puts things in a microwave that you shouldn't and gets them to light on fire, and explains why. That's because the electrons typically, or the ions in there, are being pushed around. What we know from a home example is if we take some butter and we put it in the microwave because it's too hard to eat, usually nothing happens, then it's melted. That's because the ions and the water are in the form of small droplets inside the butter. That's how butter is made up, and they can't move around very easily. Once it starts to melt, the water can move around much further and absorb the microwaves much more effectively, and then it gets hot very quickly. So these are not so important for chemistry because they're a bit big and they just move molecules and ions around in bulk. They do warm them up. 5G will warm you up if you stand very close to the tower, but it's such low energy that you will lose the heat quicker than it's coming in, or as quickly as it's coming in. It'll make you a tiny bit warmer. It's not like getting in a microwave where the amount of energy coming in is so high that you can get up to a high temperature. So if we take microwave, and we're slightly interested in microwaves but not very much, we can move into more energetic waves, into the infrared region. Infrared is everything that is we can't see, but more energetic than microwaves, shorter wavelength. However, typically we divide infrared into 2 regions: near infrared, NIR, that I've written there, and the good stuff. I've already written this because I've gone through this like 3 times. This is the part that we are interested in from a chemistry point of view, because this is where the energy from the infrared interacts directly with bonds and with molecules, and it pushes the whole molecule around, or rotates it, or it vibrates the bond. So if we think of a carbon dioxide molecule, for example, in the atmosphere trying to absorb heat from the Earth coming, the atoms in there, the carbon and the oxygen, can oscillate and they can absorb infrared that's coming from the Earth typically and convert it into heat in that case. So that is interesting to us, very important region for our part. That's why I've written a whole tower of information there. We normally think of infrared, however, from a consumer point of view, more of this near infrared. This is what we use for thermal cameras, for example. We also use it for seeing in the dark, and we also use it for movement sensors. Sorry, I was in German for a bit there. So if we take the movement sensors that at our college, for example, turn the lights off while you're in the bathroom if you don't move around fast enough, they use a near-infrared LED because they're cheap and you can't see them. They use a near-infrared LED and they're sending out little flashes and it's looking back to see what comes back, and if it changes, they switch the lights on. Likewise, if we take a camera to look at wild animals, it will typically work in the near-infrared region because it has two advantages. One, the animals can't see it, and you can see reasonably well. The LEDs are cheap. And the other advantage is, because it's not ultraviolet, it's down here, it's not going to damage anybody's eyes. So you can have them on your building to see people that are moving around at night. Those pictures that you see, night vision cameras, typically are in the near-infrared region. But now we're in the visible region. In the visible region, there's nothing special going on. It's just the wavelengths that we as humans happen to be able to see. Other animals can see very often a little bit into the ultraviolet part of the spectrum, sometimes into the infrared, but more often slightly into the ultraviolet. And for chemistry purposes, we like to lump those together. What you might know is that this kind of light interacts with molecules because of things like this. This is a pen, it's got chemicals in it, and it's blue. Why is it blue? It's blue because it absorbs red light and lets blue light come back. The red one is the other way around. It absorbs blue light and red light is left over. So where does it go? In here the energy was the energy was going into the bonds, or it was going into the whole molecules and making them rotate. In here it's going into clusters of bonds. Here it's going into the electrons in the bond themselves. Let's take an example. Let's do my favorite example first. So we've got chlorine, and if we take chlorine and we mix it with hydrogen, you can see, if you look in the rest of my videos, you can see one that's called the best experiment or something like that, where we take chlorine and hydrogen, and the electrons in this bond are actually in an energy state, in the bonding energy state down here, which is lower in energy than the original orbitals where they would have been. If we kick them with some light, kick one of them with some light, we can make it go into the anti-bonding orbital, into a higher energy orbital. It's not bonding anymore and it's actually anti-bonding, so it's worse than doing nothing, and the molecule just falls apart. In the experiment, in the demonstration, we take chlorine and hydrogen mixed together and shine light on them, and different colors of light have various effects. If it is bluer than green, so any color that's green or higher, that's up here somewhere, it will split the chlorine molecules by exciting one of the electrons in the bond into the antibonding orbital and allowing them to fall apart, and the chlorine radical then, the chlorine with one electron left over, will then go and attack some hydrogen and cause an explosion. It's quite fun. Go and have a look at that video. What you might have seen, however, is maybe a metal center. So if we take something like copper, if we take something like copper 2+, the copper 2+ ion in water is typically a hexa-aqua complex, which I'm not sure. Sometimes we teach it in inorganic chemistry, sometimes it falls by the wayside. But if we take the hexa-aqua complex, which is octahedral, oh, the sound again. Good, it was short this time. So if we take the octahedral hexa-aqua complex and we excite it with light, we can get what is called a ligand transfer, in which electrons are transferred from the orbitals, in between the orbitals in here, but typically from one of the ligands, one of the waters, to the copper. As you probably know from school chemistry, if we take this copper complex, so we dissolve copper sulfate, for example, in water, and we add ammonia, we can change it to the hexa ammonia complex, or to some, you can change some of these waters for ammonia, and it changes the color from a light blue color to a really deep blue color. That's because it's changing the energy that it requires to excite the electron into the copper. So the difference in energy is slightly different, but this is just changing it from absorbing red light to absorbing a slightly different color of red light. If we get all the way, let's check this recording, if we get all the way to the end of ultraviolet, so B and C, it's called ionizing radiation, because we can kick the electron right out of the bond into space effectively. So why is ultraviolet damaging to our skin? Damaging to our body? It's damaging to our body because the energy can be absorbed by a bond in DNA typically and cause it to break. And during the repair process there can be a mistake which can be serious. What we do to prevent that is we put a material, some chemicals on our skin which will absorb the light instead. It's obviously a problem because the chemicals that we put on our skin will tend to get damaged by the ultraviolet, but that is often solved by using a titanium dioxide particles, which can absorb the light and not get damaged. Moving up to X-rays, they have higher energy still. They've got so much energy they can't be absorbed by a bond unless it kicks the electron right out of the molecule. So it can do that because once the electron has escaped, it can obviously come out at different speeds. Therefore, unlike down here, where the molecule can only absorb photons of a certain energy, and here, where the electronic states are quantized, so that only certain colors can be absorbed. If we get too high, we can kick the electron right out, and then it can have a whole bunch of potential colors. However, these X-rays we normally see for non-bonding electrons, because they're a lot lower in energy, so they can absorb more energy before they leave the molecule. There are more energetic states for them. So if we take something like our chlorine again, for example, well, it doesn't just have the bonding electrons, which are on the outside. It also has the 1s electrons, which could also absorb the X-ray energy and be kicked up into a higher state. They can absorb X-rays. So this is no longer going to do any chemistry because the chemistry is of the bonds. This is the doing chemistry part of the electromagnetic spectrum. This part is more interesting for us because we're going to interact with the non-bonding electrons, and we can try to identify which atoms we have, which elements we have from that. Now we're interested in how we make these X-rays, or how the X-rays are formed. If we look at this process, we can see that it could go the other way around. We can have an electron, if we make a hole here, so we shoot this electron out somehow, we can drop other electrons down from outside, and that will give out a single colored X-ray. Typically the X-rays that we see, however, in an X-ray machine are not single color. In a chemistry machine, they will be a single color for a specific reason that we'll come on to when we talk about that. But in an X-ray machine, for looking through our body, They're typically not one color, not monochromatic, and they're made by shooting electrons into a metal that causes them to slow down very quickly when they get inside the metal, and the energy that they contain is given out as a broad spectrum, as sort of random colors of X-ray. Once we get into gamma radiation, we've got so much energy that even these electrons can't absorb it without something extreme happening. They would be going very fast indeed. So the electrons find it very difficult to absorb gamma radiation. That's why it passes through us, and it passes through most materials very easily. It can mostly interact with nuclei. Gamma radiation, we know from radiation. Gamma radiation we know from nuclear radiation, and it comes from particles in the nucleus decaying or being fired out and giving out a very high energy electromagnetic wave, which, as I say, can't be absorbed very easily by any of the other processes because it's far too much energy. So what do we learn from that? We learn that there's a quantum mechanical rule that when a molecule, electron, bond, or other kind of particle interacts with an electromagnetic wave, it must absorb it all or not at all. That's the part of quantization. So if we consider it to be a photon, a package of energy, and the chemical, the bond, the electron, has to absorb it all. If it has to absorb it all, it has to immediately do something with that energy. It can't just sort of wait in some magic high energy state. So it's much easier to absorb it if there is an energy state ready for it to go into. So if the electron, for example, can go from a bonding state into an antibonding state, if the electron here can go into a different orbital, if the bond vibrating can vibrate at a different frequency and absorb the energy, then it will more efficiently absorb the energy coming in. If it's too much for that, if it's too little for that, it can't do it. If it's too much for it, it can absorb it sometimes and have, for example, excess kinetic energy, but that's less and less likely, and so we see things like gamma radiation, X-rays go through most materials. Ultraviolet is absorbed by nearly everything because it tends to break bonds, it tends to interact with free electrons very easily. What I'm interested in now is cutting down our electromagnetic spectrum to the bit where chemistry happens. So let's do that. We can get rid of all of this apart from the last bit of microwave maybe. Let's get rid of it. It's less work if we don't have it, and let's get rid of most of it. Let's get rid of the gamma radiation, and let's get rid of let's get rid of part of the X-rays. And this is the bit that we're interested in. So we're interested in infrared interacting with bonds, mostly. We're interested in visible light, ultraviolet light interacting with electrons in bonds, typically. And we're interested in X-rays interacting with non-bonding electrons. Those are our chemical parts of the electromagnetic spectrum that we're going to play with.